Hello everyone, I am Mike. Nice to meet you all. Today I'm going to talk about the inverse kinematics and how the robot moves from point to point. The math take a big action on this topic, inverse kinematics. It is a method that helps to define the motion of the robot to reach the desired location. For example, to perform a surgical task, a robot arm used in medical surgery needs precise motion from the initial location to a desired location. Robot kinematics involve deriving equations to describe an analytical relationship between the joint parameter and the end effector. Once the robot joint angles are calculated using the inverse kinematics equations, the motion profile can be generated using the Jacobian matrix to move the end effector from the initial to the final location. The Jacobian matrix helps to define a relationship between the robot joint parameters and the end effector velocities. So, how we can solve the inverse kinematics? So let's see. I will introduce you to know more about how to solve the inverse kinematics. Let's go! Okay, so let's first talk about the inverse kinematics. This is a picture of the example of the robot joints. This robot has 3 joints, as you can see in this example too. For the joint E is the end effector of the robot. We have to set the target point is here, is the rate point. We have to move joint E to the target point. So what I have to do to find the angle of 3 joints to know how the robot moves. So we can see and we can solve it by many methods. And today I'm gonna talk about like 5 topics. We will start with the planar robot. It's a inverse kinematic in one plane. And next is simple humanoid robot arm. And next is the sphere hand fiber method. And the last one is Jacobian matrix. So first let's start with the planar robot. Have many methods to like solving. And for the traditional method we have 3: algebraic, geometric, and iterative. Is the combine of the optimization to solving. But now in this course, I learned only 2 methods. Is the algebraic and geometric method, which is helpful for solving the inverse kinematic. So let's talk about the first is the algebraic method. The algebraic method we will go through the planar robot. Consider a simple planar robot with the 3 links L1, L2, and L3. We can find the DH matrix or the homogeneous matrix from the forward kinematics. And you will get this matrix to find the rotation matrix and the end effector points. So as you can see here, we have Px, Py, and Pc. We have only Px and Py because it is 2D plane. And next, I define Px is the end effector in the x-axis and y is the end effector in y-axis. Yes. And theta 1, 2, 3 is the angular of the end effector. Here, singular is a theta 1, 2, 3. From here is a parallel with this one, and this is theta 3. And for theta 2, and this is theta 1. So the theta of the end effector will be here. It's the theta 1, 2, 3. And you can see that Px and Py. Px is the end effector relative to the x-axis. So Here, you can see that if L3 in the x-axis is L3 multiplied by cos theta 1, 2, 3, and for the L2 in the x-axis is L2 cos theta 1, 2, and for the L1 is in the x-axis is L1 cos theta 1. So if we plus everything together, we will get this px. And py is also but in the y-axis. And for the calculation, first we have to find the theta 2. Theta 2 is came from the px and py equation that we put px and py equal to the length of the link px, as we talked before last slide. Px is here, py is here. So you can see that if px px and py, if px minus by L3 R11, R11 is cos 1, 2, 3. So L3 cos 1, 2, 3 is here. This is L3 cos 1, 2, 3. And this one minus by this one. So we get this one. Yeah, because we cut it off. And also for the y-axis, we get only this because we cut it off. And here will be equal to the x and y, x and y points. X and y points is the point of the B points. And next, we have to make it equal to L1 cos 1 plus L2 cos 1, 2, because as we do in the last slide, L1 here is L1 cos theta 1. And this is the L2 cos theta 1, 2. So we can plus it will be equal to the px minus by L3 R11. Yeah. And we can prove that this equation is true. And after we got this, we can identify point x and point y by point x is equal to px minus L3 R11 and point y is equal py minus L3 R21. And after that, for step 1, we get all parameters that we need. So we find the theta 2. How we find the theta 2? How we can find? So first of all, we have to make the equation to be have only theta 2. So how can we find these equations? I make the algebraic method. So 2 of this equation must be powered by 2 and plus sum them together. So is it true? I will prove it. By first, I define px minus L3 R11 square plus py minus L3 R21 square equal to, and this term we leave it, and we only have to solve the second term. and we can see that. So we leave this term out. So we get 2 L1 L2 C1 C1 2 plus S1 S1 2. This one sum together, we will get cos theta 1 square plus sin theta 1 square equal to 1. And next we will solve this to be equal to cos theta 2. And from the trigonometry identity, cos 1 2 is equal to cos 1 cos theta 1 cos theta 2 plus sin theta 1 sin theta 2, and I will get cos theta 1 square. And for the next term here, I will get sin theta 1 square, and this will cut it off to be equal to 1. And also cos theta 2 will leave. So I will get 2L1 L2 cos theta 2 plus L1 square plus L2 square. And after we find out the theta 2, we will put our value that we know into the equation and get the C2. The value of the cos function should be in the range of L1 minus L2 and L1 plus L2, because for the maximum length for the robot, the L1 can be straight, full, and the longest is L1, and the length 2 can be go straight, and the maximum length is L2. So it will be the maximum length, and for the minimum is L1 minus L2. So if x and y of the equation is true, it has to be in the range of this. And next, we get cos theta 2, and we have to find sin theta 2 in order to find the theta 2, because if we got only cos theta 2 and find it by arctan, it will give on cos theta 2, it will give only in the plus the positive quadrant. So in order to find the right equation, we have to find it would be plus or 0, something like it, plus or minus something like that. So we have to use a and 2 because it will tell you what quadrant it is. And next we get the theta 2. Now we find the theta 1 by x and y. X and y is the same as we got before, and put it in here. And this is the value that we already know, so we get the theta 1. And if we get the theta 1, we find the theta 3. Theta 3 by R21 and R11 is I1, 2, 3, cos 1, 2, 3, and minus by the theta 1 and theta 2. Because this is the C, or the theta 1, 2, 3. And next method is the geometric method. It's a method that we use the geometric identity to find the length of the link, something like that. For the first one, we identify OB. Here, the line OB is the point XY, line OB, and this point is the point XY. And we can find by Px minus L3 cos theta 1, 2, 3, as we proved before. And to be different, the step of finding the theta 2, we will use the cos cosine rule to find the cos theta 2, because here is a triangle that we have the theta 2, and here we can find the cosine, we can find the theta 2 by cosine rule and get the x squared plus y squared. X squared plus y squared is a squared plus b squared. Is here and here, and minus by L1 squared minus L2 squared. And over the 2 L1 and L2. And it's the same range. The xy of us have to be in the length of L1 minus L2 to the L1 plus L2. And next is to find the theta 1. Theta 1 is the alpha of a tend to y and x, y over x. It came from this angle is alpha. Alpha is came from theta 1 plus beta. So we have to find beta. Beta is come from a cos this term, and we will separate it into two sections because our theta 2 have the positive value and negative value. So it can be two value is possible. As you can see that from this picture, we have two way of robot link can do here and here. This is a positive and negative value. And third one is find the theta 3 by sum up and minus it off. And this is the example of inverse kinematics in the planar robot. And the question given the transformation matrix and determine the L1, L2, and L3. And we get the point 1, point x, py, and theta. And b is theta 1, 2, 3. And we have to find theta 1, theta 2, and theta 3. So, first of all, the same equation as before. First of all, we have to find the theta 2, right? So, as a equation, px minus L3R11 square plus py minus L3R21 square equal to L1 square plus L2 square plus 2L1 L2 cos theta 2. And you can see that we can put px and py from here, put it to here. Okay. Minus 1.506 minus by 1, length is 1, and is cos minus 1.8326 plus and it will be equal to L1 square is 4 square, 3 square, 2, 4, 3 cos theta 2. Okay, so it will be 25 plus 24 cos theta 2. And this term I get 8.86627. Over the 24 equal to cos theta 2. And we will find sin theta 2 equal to root of 1 minus cos theta 2 square. So it will be equal to plus minus 0.92. And we get the theta 2 equal to a tan 2 minus plus minus 0.92 and 0.3694. 3694 is here. And we'll get it equal plus minus 1.192. And next, we will find the theta 1. Theta 1 will be equal to, have two cases, right? So the first case is the theta 2 is the positive. This can from a tan to yx minus a tan to L2 sine theta 2 L1 plus L2 cos theta 2. So it will be equal to 1.297 in the case of theta 2 positive, and next is 2.296 in the case of theta 2 is negative. And next is find theta 3. Theta 3 is from the phi minus y theta 1 minus y theta 2 will be, theta 3 will be equal to minus 4.3 and minus 2.9. Theta 2 is positive and theta 2 is negative. So it's so easy to get theta 2, theta 1, and theta 3. So here are all the first part of the inverse kinematics. Let's go next. Okay, let's go to second part is the Piper method. The Piper method is more general method that useful for 6-axis robot. And we will use the knowledge that we learned before to do this too. The inverse kinematic used Piper method is the method that we will use to separate the axis of the robot into two parts, but we use three methods to do it. It is the three consecutive rotational joints with the axis intersecting in the single point, which is this one, is a point of intersection. So we will start with step 1. Step 1 of Piper method is to locate the intersection, which is this one is the intersection of this joint and this joint. So this point will be point OC, and this point is point O. We will call it OC. And this is the length and the distance of the joint of the link. Step 2. Calculate by rotation matrix R and the end effector position Px, Py, and Pz. We will use a new method. It's the simple humanoid robot method. It's a method that we have to find the theta 1, theta 2, theta 3 from the end effector point and rotational matrix point that we know. We have to find the rotation matrix to calculate the homogeneous matrix to find the theta 1, theta 2, and theta 3. In this case, we will use R to put it in this equation. This equation is from OC. OC is the point here, will be point here, will be calculated by use OC equal to O. O is the point of the end effector, which is Px, Py, and Pc. And minus by the rotation matrix. Multiplied by D. D is the distance of the end arm or the end link. And K6 K6 is the unit vector of z-axis. And from this equation will allow us to know the px, py, the xyz points of the OC. We will find the x, y, z point of OC. So if we calculated this, it will be the output will be like this. So we can know the px, py, and pc. And next step is step 3. Now we get px, py, and pc, or the point of x, y, z at point OC. So now we have to solve the inverse kinematic equations to find the theta 1, theta 2, and theta 3. Theta 1 is come from a tan 2 of py plus d cos theta 1 divided by px minus d sine theta 1 is here. And from this equation, we will get the theta 1. But actually, we didn't know the cos theta 1 and sine theta 1. So we have to change it by the geometry identity from this to make this equation to find the theta 1, because we already know px, py, d, and d. Next, now we have theta 1, so next we will find the theta 3. Theta 3 is come from here, a tan sine theta 3 by cos theta 3. So at first we have to find sine theta 3 and cos theta 3, which cos theta 3 is come from this and sine theta 3 is come from this, so that we can find the theta 3 for sure, because we know all value above. L is the length of the link. Yes. Px is the length from the base point to the end point, and h is length of this, so this will be pz minus h. So the theta 2 is come from a tan 2 of pz minus h by the square root of px squared plus py squared minus d squared, and minus by the length of the second link, multiplied by sine theta 3 and over the L1 plus L2 cos theta 3, and we already know every value, so we can find it theta 2. So now the all theta is supposed to find out every single theta. And next we will use the theta 1, 2, 3 that we got before to find the theta 4, 5, 6 by the new method, which is called the sphere hand method. Sphere hand method is one method that we could use to find the inverse kinematic. And this method we will first introduce you to know that the theta 1, 2, 3 that we just calculated can define the rotation matrix. So we will create the rotation matrix this, and next we will find the homogeneous matrix, this one. And as you can see that you will see this value, that is the single cos theta 2, so that cos theta 2 is come alone, so we can find theta 2 first because it's the easy one. And for this is the method we can find. But it has a rule that sine theta 2 could not equal to 0 and cos minus cos theta 2 that equal to R33, this one cannot equal to 1. Yes, and if the cos theta 2 minus cos theta 2 equal to minus 1, it will cause a robot singularity. And for this case, I have to find the sine theta 2. So I will use this equation to find sine theta 2 because this one is cos theta 2 square, and cos theta 2 square plus sine theta 2 square is equal to 1. So that's why this equation is used to find the sine theta 2. And next is step 5, solving the inverse kinematic equations, finding the theta 4, theta 5, and theta 6. For this step, we already find this one because we got cos theta 2, so we will got sine theta 2 also. And it will separate and divided into two cases. The first case is sine theta 2 is the positive value, and the second case is sine theta 2 is negative value. And remember that sine theta 2 is not equal to 0. For this case, if sine theta 2 is more than 0, the theta 2 can be found by this equation, theta 1 can be found by this equation, and theta 3. Yes, and this method is such a very easy method and quick method, but we have to aware of about the S2. And if S2 is the negative value, the method will be, the equation will be changed a little bit, like we have to use the minus. After we find theta 1, theta 2, and theta 3, and we get theta 4, theta 5, and theta 6, so it will be all calculated and it can use for the robot moving now. And this is the sample code that we use MATLAB to identify the rotation matrix by finding by the theta x, theta 1, theta c. And this one is used to identify the px, py, pz in OC position. And for the last part is the Jacobian matrix. What is Jacobian matrix? The Jacobian matrix is the matrix that helps to define the robot velocity. And I will show you how to make it by the easy one. Okay, so let's see about the Jacobian matrix. This one is the table of making the Jacobian matrix for the three-joint robot. First of all, I will tell you what parameter we'll use in the Jacobian matrix. So you can see that it have the 6 row with the 3 columns, 6 row with the 3 columns, and I will separate it into 3 because it have the 3 parameter. First, in the first column we will identify the velocity, the linear velocity. And the last 3 will identify the omega or the rotational velocity. And it also have the 2 columns left, and this 2 columns will identify this first will identify the prismatic joint, and this one is revolute. And the first example of the Jacobian matrix is this one. As you can see that we have the 3 rotational matrix, which identify, the first one identify the linear velocity, and this one the prismatic joint. And why is it a prismatic? Because it's moved in the linear velocity. You will see more detail in this picture. Here is the axis of the robot that identify more like more more obviously for identify the rotational. This one, as you can see that D1, D2 and D3 is in the this one is in the z-axis and z-axis. So it will have only the prismatic joint. And you will have the omega x, y, z equal to 0 because what? The rotational velocity is equal to 0 because it has only the linear velocity. And now we will know the Jacobian matrix and how to use the Jacobian matrix to find the velocity of the robots. Thank you for listening. Hope you enjoy my video. Thank you.